Hi, this is StephenHowland. Today I'll be making my second presentation over some material in section 6.5 for Dr. Insall's linear algebra class. The goal of this presentation is to understand that you can transform any kind of function into standard form, and then you can find the least squares solution. And with this solution, you're able to form a function that is the approximation of all the given data, I should say. So if you recall when Boystrand had that problem in class where we were given like 5 data points and we had to come up with an n-1 polynomial, so a fourth order polynomial, to represent a line that passed through all of the points. Well, this is a similar problem. However, let's pretend that we have like 10 points and we know for sure that it needs to be an x squared, like a second order polynomial. Okay, so because we have so many points and only so many constants, we have to use the least squares solution. Looking at the top of the page for the first slide, I'm saying, let's say we have y equals a2x squared plus a1x plus a0. So we have 3 constants. If for some reason, like I said, we have 10 data points, which is greater than the number of constants, there's going to be no solution that will pass through all of the points. But we can find a y hat, which is an approximation of y, and that'll have a solution. You can read the definition on page 360 on section 6.5 in your book. And you can also read how it better explains it, but ultimately what you need to know is that you can form theorem 13, which says the set of least squares solutions of ax equals b coincides with the non-empty set of solutions of the normal equations a transpose ax equals a transpose b. Okay, so we said least squares solutions helps us find a function to approximate something. Okay, let's say that we're trying to come up with a function that represents the position of a particle as it changes with theta. So it'll be a polar function, and let's say it models the function r equals a2 cosine squared theta plus a1 sine squared theta plus a0 cosine times 30 theta. Why did I pick this model? Well, if we have a2 and a1 equal 5 and a0 equals 1, this function comes out to be like sort of like a circle that has an oscillating radius of 1. And so, you know, maybe this particle is like an electron orbiting a nucleus, and we know that it vibrates while it's orbiting this nucleus. And we're just gonna assume that it follows this path, but we don't really know. We're just guessing. Okay, so for our particle, let's say our instruments were able to collect 4 data points, which is pretty pathetic, and these data points were in the Cartesian xy plane. Time is not a factor here. We're just worried about its position as it rotates around the origin. And so, okay, so looking at the second page, we have the points 3, 17, 4, 16, 5, 10, and 10, 7. The red and blue markings I'll explain in a bit, but you can see the black dots are plotted on the xy plane. So again, we're trying to find an r theta that is the least square solution of r equals a2 cosine squared plus a1 sine squared plus a0, and we're hoping it's going to look something like that blue line where it passes nicely through most of the points. It looks like a function that we can follow, and I've shown in the red that, and this is from the end solution, that the reality is not like the blue. It's terrible, chaotic. So, but we'll come back to that, and you'll see why. So the first step is to convert x, y into polar. We have r equals square root of x squared plus y squared, and theta equals the inverse tangent of y over x. You can see the r and corresponding theta values I calculated from the given 4 xy points. Then we need to convert the function to standard form. So I've rewritten our function we're trying to find the least square solution of, and I've written it into standard form where ax equals b. The next step is really simple. It's just plugging in the data. So this is kind of like a second order polynomial because you have three constants, but as you can see, like, you don't need to have, like, your x squared term can be cosine squared theta, and your x term can be sine squared theta, and your your 0th term can be cosine of 30 pi. It really doesn't matter, just as long as you include those functions when you plug in the data. And I'm going to save my A matrix to matrix A in my graphing calculator, and the B matrix to matrix B. The third step is to find the non-empty set of solutions of A transpose A x hat equals A transpose B, just like theorem 13. And so we'll take our A matrix, turn it into transpose multiplied by A, which is multiplied by x hat, and that equals A transpose multiplied by B. I show what the new A x hat equals B new looks like. And from here, the last step is just row reducing this augmented matrix to find x hat. And to save time and reduce error, I'm just using the TI-84 operations already built in. And I show the exact command I use to eliminate any error or rounding. And this row reduced matrix gives us A2 equals negative 77.4, A1 equals 49.6, and A0 equals 55. So this is great. This is our solution to the function. This is our least square solution. And with this, we're gonna plug it back into that initial function to see what it looks like. At this point, A2, A1, and A0 are just numbers. We don't know if the function is going to look like we were hoping it was going to look like, or if it's just going to be complete garbage. So we see what our function looks like with A2, A1, and A0 plugged in, and we can plug in the same theta values as our given points, and you can see that I've plugged it in and I've written it down that the corresponding R value is actually fairly close to what the initial data point was. 7.263 to 7.919. It's only 0.5 off. The next one's only 0.8ish, 0.6. So it's not too bad. But what happens when we go just 1 degree beyond those theta values? Well, our radius just blows up. So going from theta equals 79.992 to 80.992, our radius goes from 17.9 all the way up to 46. For the other points, that drops down to -4, go from 11 all the way to -11, and from 12 to 21. And what this is showing us is, without even graphing it, we can tell that our function, our polynomial regression function is chaotic. It's terrible. And then I kind of went back onto wrote in red pen on our initial graph, like what this solution actually looks like. And if you want to plug it into your graphing calculator, you'll see it's no longer that beautiful circle oscillating, around the edges. It's just like this explosion of lines. And so we can conclude that, while our approximation lies very near the given points, beyond the theta values, like, the approximation is terrible for interpolation. Like, there's no way you can predict any movement with this. We were hoping for something that kind of looked right, made sense. Certainly that didn't go into negative radius values. I mean, does that make sense? So we need to either have more data points or simply a different model function. And coming up with model functions is something that all kinds of engineers and physicists are trying to do today for anything. I mean, because if you can come up with a function that correctly models the behavior of a system, then you can predict what its behavior will be in any future time. That's interpolation. that's a different subject, but the application of building these accurate functions is unlimited. Lastly, I'm going to propose a problem to prove that the accuracy of a regression function can change with respect to either of the two modifications of either more data points or a different model.